the exact same little segment that we had at the top of 6.1. It says that a circle is a set of all points in a plane that are equidistant from some center point, right here. And that point is also how you name a circle. So if that was point P, this would be circle P, and we denote it just like this. A segment whose endpoints are the center and some point on the circle are a radius, and a chord who has both endpoints on the circle and goes through the center is called a diameter. So a diameter is just a type of chord because it has both endpoints on the circle, but specifically goes through the center. All right, so then we go on to say that when a minor arc and a chord share the same endpoints, we call the arc of the chord. So for example, this chord is the diameter, right? This arc has the same points as the diameter, so that arc is the arc of the diameter, that specific chord. It also says that a polygon is inscribed if each of its vertices lies on a circle. The polygon is said to be inscribed in a circle. So if you guys remember, also on 6.1, we had a circle that had some sort of shape on the outside, right? And that was circumscribed if all those lines were tangent to the circle. But they're saying the opposite here. They're saying that you have some circle with some sort of a shape inside of it. Then that shape has been inscribed in the circle. Okay? All right, so here are our 3 theorems for today. So remember, from now on, once we know what these 3 rules are, we can mark these on any of our circles. So the first one says, in a circle, or if you have 2 congruent circles, 2 minor arcs are congruent if and only if their corresponding chords are congruent. So the minor arcs here would be like AB and CD. They're saying those 2 arcs are congruent, so the same size, if their chords, which are the ones that go from the same endpoints, are congruent. If those 2 chords are congruent, the arcs are congruent, and vice versa. The second one says, in a circle, if you have a diameter, which remember our diameter is a chord that goes through the center, if it's perpendicular to a chord, so you know that it forms that right angle with some other chord, they're telling you that it bisects the chord. What does bisect mean? Very good. So this chord has been split into 2 congruent pieces because it's perpendicular. So if you know that it forms that 90-degree angle, you're going to know that those 2 pieces are congruent in size. Okay? All right, and then the last theorem we have says in a circle or in congruent circles, 2 chords are congruent if and only if they are equidistant from the center. So if they tell you that this segment and this segment are congruent in size, then you're automatically going to know that this segment and this segment are congruent in size. So if they're the same distance away from the middle, then those 2 chords are the same size. Okay, so now that we know that information, let's flip it over onto the back and look at a few examples where we can apply these rules. All right, so it says in circle P, we know that PQ, which is this segment here, is perpendicular to RM. So from P to Q is perpendicular to RM, meaning it forms a 90-degree angle. So part A says to name an arc that would be congruent to the arc QR. So here's the arc QR. What arc is going to be congruent to that? QN. Good. Okay, so we can say that it would be RQM. Our reason would be because PQ and RM are perpendicular. So because these were perpendicular, we knew that that meant those two pieces were congruent, according to that second theorem from the front page. And then we were also told that if the chords were congruent, then the arcs were congruent. Right? Okay. B says if PR is 13, so this little segment here has a length of 13, RM is 24. So this whole line is 24, then what's each section there? 12. They want us to find the length of PO, this little line segment here. So how could we maybe find that missing side there? Right, Pythagorean theorem. And we could use Pythagorean theorem, but this is also one of our triples. Can somebody tell me what that missing side should be? Good. So x equals 5 because this is a Pythagorean triple. Good. All right. And the last one in this section says to name a segment that would be congruent to PM. So what's going to be congruent to PM? Yeah, PR. Why? What kind of lines are those two? Right. Because both are radii. Very good. All right. So let's look here at example 2. Okay, example 2 says suppose a chord of a circle is 10 inches long. Okay, so this would be the chord that's 10 inches long. But because it's perpendicular, they said that we already know that's going to split it into two congruent segments of 5 and 5. Okay, and then it says it's 12 inches from the center of the circle. So from the center of the circle to that chord is 12. They want us to find the length of the radius. So again, what would we do to find the missing side? Pythagorean theorem, right? And this is Pythagorean triple, actually should be the same Pythagorean triple, so what should R be? 13, good. All right. Number 3 says suppose the diameter of a circle is 30 centimeters. So they didn't draw a circle for us this time. We're going to draw our own. Okay, so we've got a diameter that is 30 centimeters. So here's my center. Here's the diameter. It goes all the way through. Okay, well, if the diameter is 30, what do I know the radius is? 15. Okay, so I automatically know that both of these are 15. Okay, and then it says a chord is 24 centimeters long. So kind of like up above, we've got some chord, which just means it goes from one edge of the circle to the other, that's 24 inches long, or 24 centimeters long. Okay, well, with the way I've drawn this here, if I was to draw a line directly up, that radius that I just drew in is what to the chord? Perpendicular. And if it's perpendicular, what does that mean about this section and this section? Congruent. Okay, and I knew the chord was 24 centimeters long, so what does that make each one of those sections? 12. Okay, and they want us to find the distance from the chord, which is here, to the center of the circle. So I'm looking for the length of this piece here. So that's not a radius because it doesn't go all the way to the edge. So we are going to have to solve here. What am I going to do? Pythagorean theorem again, right? So I'd have my x squared plus 12 squared as my a and b, and then our hypotenuse c is 15, right? Also one of our triples, what do we get for that missing side there? 9, right? Because we could have simplified the numbers down. centimeters. Okay, last one. This one says to find the length of AB. So AB is a chord because both endpoints are on the circle. Okay, so we know that the radius is 6. I could also draw another radius from here to here, right? And if this center, or if this arc is 120 degrees, how many degrees is this angle here? 120 as well, okay? I'm going to need to find a piece of this line. In order to do that, I'm going to need to draw in something perpendicular to it so that I can actually have something to solve. So, if I draw in a perpendicular radius here, if that angle was 120, what did I just split it into? Two 60-degree angles, okay? So this is 60. We know this is 90. So how many degrees is this one up here? 30. Okay. So which piece do we have? The 2x, the one across from the 90-degree angle, right? We know that across from that 90-degree angle, we label it 2x, and they told us that that piece was 6. So what would that mean the length of x is? 3. Okay. We label that across from the 30, but we're trying to figure out how long this chord is. So I need the part across from 60. What do we label the side across from 60? X squared root of 3. And if x is 3, then that means this piece is 3 square root of 3, right? But keep in mind, that's only from here to here, right? But what do I now know that the length of this piece also is? 3 square root of 3. So AB is going to be equal to 2 times 3 square root of 3. And what is 2 times 3 square root of 3? Very good.